This is the third in our series of lectures on the principle of mathematical induction, and in this one we'll do our first example of a result proved using the principle of mathematical induction. So let's begin by observing the following calculations. So what I'm doing in this sequence of calculations is I'm calculating the sum of the first few odd natural numbers. And we notice that when you add the first two of them together, you get 4, which happens to be a perfect square. When you add the first 3 odd natural numbers, you get 9, which happens to be 3 squared. When you add the first 4 odd natural numbers, you get 16, which happens to be 4 squared. So there seems to be some pattern here, and so we might be willing to conjecture on the basis of these calculations that the sum of the first n odd natural numbers is actually n squared. Let's write down in symbols what that says. Our conjecture says that for every natural number n, if we add up the first n of the odd natural numbers, we get n squared. So if k is equal to 1, you'll notice 2k minus 1 is 1. So the very first term is the first odd natural number 1. There are clearly n such terms because k is running from 1 to n, and every one of these is odd. So that's our conjecture. It concerns a whole sequence of open sentences, namely for each n, this is an open sentence about that n. And so what you want to do is you want to prove that every one of these open sentences is true, and so it's really perfectly set up to make use of the principle of mathematical induction in order to do it. So what I'd like you to do is put your video on pause and see if you can write up a formal proof of this using the principle of mathematical induction. So you should begin by telling us that you're going to use principle of mathematical induction. You should have a basis step, you should have an inductive step, and you should fill in all of the details of those steps. Okay, so give it a try, and when you come back you can compare your proof to mine. Okay, so here's my proof. I begin by saying that for each n in the natural numbers, we're going to let p of n be this open sentence. And then we're going to prove that p of n is true for all natural numbers n using the principle of mathematical induction. So in the next paragraph, we call it the basis step. And we have to verify that p of 1 is true, and so we write, since the summation of 2k minus 1 as k runs from 1 to 1 is defined to be the very first term in the sequence. In other words, it's 2 minus 1, which is 1, and 1 is the same as 1 squared. It follows that this statement is true if n is equal to 1. Now we come to the inductive step. We give ourselves a generic natural number, and we assume that p of n is true. In other words, we're assuming this equality is true. We have to show that p of n plus 1 is true, and so we write the summation of 2k minus 1 as k goes from 1 to n plus 1. So that's the left-hand side of our conjecture, in which we replace n by n plus 1. Now, what is the formal definition of this? Well, using the inductive definition of summation that I introduced in the previous video, it's the sum from 1 to n plus the very last term, and the very last term is obtained by replacing k by n plus 1. So it's this. Now, this sum here is n squared, and that's what we refer to as the inductive hypothesis. That's the assumption that the formula is true for n. And 2n plus 1 is precisely what this is. That's just a calculation. 2n plus 2 minus 1 is 2n plus 1. Then you notice that this is a perfect square. It's n plus 1 squared. And so I've proved that this formula is true if we replace n by n plus 1. So that proves that p of n plus 1 is true. So that's the conclusion of the inductive step. And so we have the right to say that by the principle of mathematical induction, we conclude that p of n is true for every n in the natural numbers. You'll notice one important thing that I include in my proof is at the point where I make use of the inductive hypothesis, in other words, the assumption that p of n is true, I want you to focus on that in your proof, and I want you to write that down, because that's a key step in the proof. So I want you to do that for every single one of your inductive proofs.